Okay, in this video we're going to talk through the 2017 and 2015 AP release problems that are related to KSP. And if you look at the 2017 exam, we are answering some questions about magnesium hydroxide, and we're given the value of the solubility product constant for magnesium hydroxide. We're given that right here. And if you look at what question A is asking us for, it's asking us for the number of grams of magnesium hydroxide that is dissolved in 100 mils of a saturated solution of magnesium hydroxide. So whenever a question is talking about a saturated solution and I'm given a KSP value, I want to think about this chemical equation right here. The equation for the dissolving of solid magnesium hydroxide in water. When it does that, it breaks apart into these two ions, and we are given the KSP for this reaction. It is 1.8 times 10 to the negative 11th. So this looks like it's a fairly insoluble solid. We're not going to make very many aqueous products because our K value is really small. Okay, and I'm being asked to calculate the number of grams that will dissolve in 100 mils of saturated solution. So I may not have encountered a problem like this before, but I'm being asked about how much of something dissolves. So a good first step would be to calculate the molar solubility. So to do that, I'm going to write out my ice chart, and we are looking at dissolving this in some water. So it starts out as 0, and you're going to form some ions in a 1:2 ratio. Then I'm going to go over them. I'm going to, let's write out our K expression. KSP is magnesium times hydroxide squared, and then I'm going to plug these values in to my K expression, 1.8 times 10 to the negative 11th. This is x, this is 2x squared. I end up with this equation right here. And if I solve for x, if I stop and plug this on my calculator, then the value of x is 1.65 times 10 to the negative 4th molarity. Okay, and this is my molar solubility. So this is basically how much of the solid dissolves. Of solid dissolves. That's what my molar solubility represents. And that's not what the question's asking me for. If you look at the scoring guidelines, you earned 1 point for calculating the molar solubility, but you didn't fully answer the question yet, because the question doesn't ask for a molarity, it asks for a number of grams per 100 milliliters. So there's two steps we need to think about. So first, we've got a molarity, 1.65 times 10 to the negative 4th molarity. Remember, molarity is moles per liter, and I am wondering about a 100 milliliter solution. So that's 0.1 liters. So if I do that calculation, that will tell me how many moles of magnesium hydroxide dissolve in that 100 mils of solution. And when you do that, that's 1.65 times 10 to the negative 5th. But the question is asking me how many grams dissolve. So now I have to do one more step, kind of running out of room here, and convert my moles into grams. So it's 58.32 grams per mole, and that's nice. We're given the molar mass. We didn't even have to take the time to calculate it. So when you do that calculation there, you should end up with 9.6 times 10 to the negative 4th grams of magnesium hydroxide. You could also write that as 0.1234. You don't have to use scientific notation. Either way works out well. So this is the final answer for the problem. So it's a little different variation on molar solubility, doing a little bit extra molarity math with it at the end. Okay, part B is not an equilibrium problem. It relates back to lattice energy. So if we look at we're going to compare the lattice energy of magnesium hydroxide and strontium hydroxide. So they're both ionic compounds, and we are considering the lattice energy has to do with the attraction between the ions in that lattice. So you're comparing the attraction between the strontium ion and hydroxide ion versus the magnesium hydroxide ion. And if you look at these two values, it looks like magnesium and hydroxide have a stronger attraction to each other, and strontium hydroxide have a weaker attraction. And thinking about Coulomb's law, remember Coulomb's law tells us that the attractive force is proportional to the charge of the two particles divided by the distance between them. So if we compare magnesium hydroxide and strontium hydroxide, the charge of the two particles are the same in these. It's both a +2 and a -1 in both conditions. So it must have to do with the distance between them. And if we look up on a periodic table, we will notice that the strontium ion is larger. Okay, so this is a larger ion. It's like, if you look at the periodic table, it's got more shells. And when you've got a larger ion, then that's basically like the distance between them is larger. So you're going to have a weaker attractive force. So larger ion means like larger distance and weaker attraction. So that's what's going on there. So it's a good thinking back to Coulomb's law. Coulomb's law is really important when you're explaining periodic trends like ionization energy, atomic radius, and it's also important when you're thinking about lattice energy as well. And now let's look at the 2015 one. So 2015 has to do with the solubility of calcium hydroxide. So the first question is, write the balanced chemical equation for the dissolution of calcium hydroxide in pure water. This is a fancy word for, dissolving. Okay, so we're looking at what happens when you stick this solid in water, and it's an ionic compound, so it is going to break apart into its ions. And this is actually a substance we've looked at a few times already, so this might look familiar. So that's your answer to question A. That was a one-pointer. Cool. And then B, calculate the molar solubility of calcium hydroxide, but not in pure water, in a solution that's 0.1 molar calcium nitrate. So this is a solution that already contains some calcium ions and some nitrate ions in it. So when we set up our ice chart, I'll just do this right here and right on top of this. Usually our initial concentrations of ions are both 0, but in this case, we are actually starting out in a solution that's 0.1 molar calcium ions. There's no hydroxide ions. And then we're going to go through and fill in our change. So this is x, this is 2x, this is 0.1 plus x, this is 2x. You go and you write out your K expression, which is going to look like this. So we got calcium times hydroxide squared. Then you plug in your values. So 1.3 times 10 to the negative 6. Your calcium ion concentration is 0.1 plus x. Your hydroxide is 2x, and you're going to square that. And then as we simplify this, because K is small, we can assume that this difference is insignificant. So 0.1 plus x, we can assume that is just 0.1. And then 2x squared, that becomes 4x squared. So we should be able to work our way through here and solve for x. And when you do that, you should get that x is 0.0018. And that is what we're looking for when someone asks us, what is the molar solubility? Again, what that is representing, x, is how much of your calcium hydroxide dissolves. Because for every 1 calcium hydroxide that dissolves, you make 1 calcium ions. So the value of your x, the amount of calcium ions made, is equal to the amount of calcium hydroxide that dissolves. So that is the answer to question 2. That was a 2-pointer. You got a point for the showing your work with the correct setup and a point for the final answer. And then if you look over here at part C, we're connecting it back to particle level representations. And so we want to show what this would look like at a particle level, show some water molecules, what these calcium ions would look like. So your water molecules look like this. Looks like a little Mickey Mouse version here. And in this little Mickey Mouse, you want to remember water is H2O. We've got 2 hydrogens for every 1 oxygen. The oxygen's more electronegative than the hydrogen. If you look at your periodic trends, that means that the electrons are going to be pulled towards the oxygen side. And that means the hydrogen side of the molecule is going to have a partial positive charge. The oxygen side will have a partial negative charge. So when you draw how these water molecules are going to interact with their calcium, you want to show the negative side of the water facing the calcium ions. That's what they're looking for in this problem. Okay. So thanks for watching. Let me know if you have follow-up questions.